Hi, my name is Darren Chang, and my poster project is on the evolution of group theory. In the main article that I read, called The Evolution of Group Theory, a brief survey by Israel Kleiner, presented the development through 5 stages that I will be discussing today. The stages are sources of group theory, development of specialized theories of groups, emergence of abstraction in group theory, consolidation of the abstract group concept, dawn of abstract group theory, and divergence of developments in group theory. Why did group theory evolve? There are a few motivations for group theory to evolve: an increased concern for rigor, the emergence of abstraction, the rebirth of the axiomatic method, and the view of mathematics as a human activity, possible without reference to or motivation from physical situations. There are 4 major sources in the evolution of group theory that we will go more in depth by each mathematician and their contributions. First one being classical algebra, second one is number theory, third is geometry, and the fourth is analysis. Development of specialized theories of groups. We broke it down into 3 groups: permutation groups, abelian groups, and transformation groups. So permutation groups. In 1770, Lagrange studied permutations as well as the solutions of polynomial equations such as the quartic and the quintic. And then Galois pointed out that the resolvent was related to the existence of a normal subgroup of prime index in the group of the equation. In other words, that the existence of the resolvent equations for the quartic and the quintic had to be related to if whether or not there was the existence of a normal subgroup of the prime index of the group of the equation. In 1850, Cauchy introduced the permutation and cyclic notation we use today. He defined the product of permutations, degree of a permutation, cyclic permutations, transposition, and the identity permutation as a permutation. And this is Cauchy to the right. In 1870, Jordan explicitly established the idea of isomorphisms and homomorphisms. I found this quite interesting as this was a lot of stuff that we actually covered in our class this semester. And this is Jordan on the left. Next, you have abelian groups. In 1870, Kronecker defined an abstract operation on a finite set of arbitrary elements which satisfied certain properties. Here he is right here. In his definition here, he says let theta prime, theta double prime, and theta triple prime dot 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 be finitely many elements. And then he goes on to discuss that if theta triple prime is equal to the function of theta prime and theta double prime, and that same function is equal to if you switch the order of theta double prime and theta prime. And then he goes on to say that if theta double prime is different than theta triple prime, then that means the function of theta double prime with theta prime must be different than theta prime and theta triple prime. And then he says you can replace the operation of the function of theta prime and theta double prime by just multiplying the 2 elements together. Thus, they use the equivalence symbol to define the equivalence of theta prime dot theta double prime being equivalent to theta triple prime. And that's how he defined the function theta double prime being equal to theta triple prime. And here were a set of properties that he also discovered. So the first one relates to the order of an element. So for theta being some element in a set, and if that element to k power is equal to 1, the identity element for some positive integer k, and if that is actually the smallest possible number for theta to the power of k to be 1, then he says it belongs to k. In other words, k is the order of the element theta. And he goes on to say that if k is the order and there exists another integer m when taken to the power of theta taken to the power of m equals the identity, then k divides m, and that's kind of true to what we discussed in the class. And his second property is that if an element belongs to K, then every divisor of K has an element belonging to it. The third one is if theta and theta prime belong to K and K prime respectively. So K and K prime being the orders of theta and theta prime. And if those two orders are relatively prime, then the order of the two elements taken in the operation will be the two orders being multiplied together. And then here he has this fourth property, which I've been trying to wrap my head around. Uh, from what I'm getting from it is that if you have the list of all the elements in your group and these numbers n1, n2, n3 are the orders of each respective element. And if each one is divisible by its successor, then the product of the orders is equal to the total elements of the set. But that doesn't really make sense to me as uh, the product of the order of each element being equal to the order of the set. Transformation groups. In 1884, Klein finally solved the quintic equation using symmetry groups of the icosahedron. He discovered a connection between the groups of rotations of the regular solids, polynomial equations, and complex function theory. And he's also the creator of the Klein-4 group, which we study very often. In the early 1880s, Lee studied continuous transformation groups. He connected the theory of continuous transformation groups to be of use in geometry and differential equations. And to me, this is a huge part in the development of group theory because now it connects it to other branches of mathematics, which will motivate other mathematicians to continue to study it, not just for the sake of group theory, but for their own specific branches, such as geometry and differential equations. 3. The emergence of abstraction in group theory. In 1854, Cayley gave the first abstract definition of a finite group. And here he says a set of symbols, I being the identity element, alpha and beta, dot, dot, dot. He says that if you take the product of any two elements in any order that you want, you're going to get back another element in the set. So he's defining the closure property. And then he goes on to say that these elements aren't usually commutative, but they must be associative. And then his third statement here is talking about multiplying a group on either the left side or the right side by one of the elements in the group, and you just get back the group. And this is kind of what we've been doing with left and right cosets. So here's a quote by M. Klein, which I found really interesting. Premature abstraction falls on deaf ears, whether they belong to mathematicians or to students. And this is really prevalent in Galloway's time when he was coming up with a lot of his group theory, because there wasn't a lot of foundation built when he came up with many of his early ideas. So it kind of just went over most of the other mathematicians' heads. And I like the second part of this quote, or to students, because as someone who wants to be a teacher one day, I can see how talking about these abstract ideas to students who are just learning about the basics for the first time will just make no sense, and they're just gonna zone out and just block it out like if they were deaf. Emergence of abstracts. In 1882, Weber gave a modern definition of an abstract finite group. And here in his definition, he talks about the closure property, but does it in a more symbolic way. And then the second one here is the associative property. And the third one was one that hasn't been mentioned before, but it's essentially the left and right cancellation laws. So that if theta and theta r equals theta theta s, or theta r theta equals theta s theta, then you can just cancel out the thetas on the left or right side to get theta r must be equal to theta s. In 1882, Von Dyck gave a formal definition of an abstract group, both infinite and finite. He introduced generators and defined relations. A quote I pulled from the article is he said that all isomorphic groups are included in a single group. So this is what we've been studying, and on that huge list of groups that are isomorphic to each other, how there's only certain groups of certain orders, and the rest of them are isomorphic to them. So for example, groups of order 4 are the Klein 4 group, Z4, and Z2 cross Z2. And he was also the first to explicitly require the existence of an inverse in the definition of a group. So we're continuing to build on the definitions and properties of a group that we use today. Consolidation of the abstract group concept and dawn of abstract group theory. Concepts and results introduced and proved in the setting of concrete groups were now reformulated and reproved in an abstract setting. So as all these mathematicians built more and more on top of these foundational ideas, they were able to also put more rigor into what they were doing and just reprove these things instead of in a non-abstract way, but in an abstract way. And studies originating and based on an abstract setting began to appear. In 1889, Holder first introduced the abstract notion of a quotient group, and then in 1893, he also introduced the concept of an automorphism on a group. And again, this is super interesting to me because these are all things we've talked about in class this semester. And finally, we have the divergence of developments in group theory. Finite group theory, extensions of certain results from finite group theory to infinite groups with finiteness conditions. Group presentations, otherwise known as combinatorial group theory. Infinite abelian group theory. Schreier's theory of group extensions, algebraic groups, and topological groups. And here's a timeline of kind of what happened throughout history in the development of group theory. So as you can see, it's all started off with the sources of classical algebra, number theory, geometry, and analysis. And then from these sources, they became specialized theories. Algebra became permutation groups, number theory became abelian groups, geometry analysis helped create transformation and infinite groups. And then postulates came out for finite and infinite groups. And then studies in the abstract setting began to appear. And then finally, actual books and texts began to appear on groups. And here we are today with the divergence of group theory and all of the different types. And here's my works cited.